changes? Are you going to be a change man?
I like that font midterm.
Fair enough. Okay. All right, folks. So we're going back to chiral centers, and we're talking more about chiral centers. Okay. So again, what is chirality? What's the easy way to sort of sum that up? Like handedness, right? Okay. So similar to your hands. Well, that didn't do what I wanted it to. There we go. Okay, so when we look at chiral centers, sort of the easiest way is to use our hands to mimic these things. You can actually use your 3 fingers. If you want to use a model kit, that's actually very helpful. Okay, it makes your life a little easier. Did everybody see that I put up a model kit that's about 20 bucks? Okay. That would be my recommendation because it's very compact. It's relatively decent price, and it's quite useful. Okay. Okay, so again, if you reflect a chiral center or a stereocenter through a plane or a mirror, what would you expect? You'd expect a reflection on the other side, right? And then, are they superimposable? No. If they're a chiral center, if they're a stereocenter, it needs to be non-superimposable. Now, one of the factors that makes these a chiral center or a stereocenter is the fact that they are an asymmetric atom. If they have a plane of symmetry in it, that means that there's 2 things that are the same on both sides, isn't there? Can everybody envision that okay? Yeah, kind of? Okay. The very fact that they'd have a plane of symmetry through it would preclude the entire notion of it being a stereocenter or a chiral center, okay? That would actually stop that. And so if you're looking at a tetrahedral atom like most carbons are, that's going to be 4 or more different substituents. So if you have 4 different substituents around a tetrahedral atom, then that's going to end up being a chiral center, okay? Now, let's go ahead and look at drawing in, getting the other chirality out of these things. Now, how you're going to do this is if you have one of the chiral centers, so right here we have one of the chiral forms right there, right? Okay. And if we want the other chiral form, what we're going to do is we're going to take any 2 atoms that's around that chiral center, and we're going to swap them. Okay? The easiest ones to do is always the ones that are in the plane. Everybody see that okay? The one in the plane of the paper is always the easiest one to do. Right? If you've drawn one of them out, then all you got to do is erase those 2 and switch them. Man, that had no effect at all on the temperature in here, did it? It's actually kind of impressive. All right. So, for example, right here, we go ahead and swap the W and the X, and that's going to give us 109.5 rotation, would cause us to no longer match up with it. So, see, we've actually generated the other stereocenter, the other chiral. Okay? Form. So again, these are some different examples of stereocenters. Notice in here that the first one attached to each of these is a CH2, isn't it? See that little one with the star in the middle there? Okay. Notice the first atom attached to its carbon every time, isn't it? Yeah. But all that matters is that they are overall different groups that are attached, that they are not symmetric groups. Okay? And so, for example, we have a methyl here, an ethyl over here, and 1, 2, 3, propyl. Right over here, right? And so each of those is different. We can tell the difference between them, and therefore that middle center is a chiral center, isn't it? Okay. Does anybody have any questions right there so far? All right. So let's go ahead and look at this one right here. Here we have two chiral centers. Can you see those little stars? All right, now, is there a plane of symmetry in this? It's kind of tempting, right? You have chlorines on both sides, right? Yeah, they're in different sides of the plane, right? One's coming out towards you, one's coming away from you. They're never going to overlap, are they? Yeah. So it's not actually a plane of symmetry, is it? Yeah. And so both of these are chiral. Note if we look at the two different sides, on one side we have two carbons until we get to a chlorine right here. And the other side we have one carbon until we get to a chlorine, right? And so you have 4 different groups on each of those carbons as well. Okay? Okay, did I confuse anybody or did anybody get caught up? Uh-huh.
Why is the third carbon also not
A chiral center? Because it has two it has a CH2, 2 hydrogens. And so that one actually does have 2 hydrogens, which makes it so if you rearrange it, it would be the exact same. You can reflect back through. Or another way of looking at it is it actually does have symmetry. Okay? In this case, it would actually have what's called rotational symmetry, but that's an inorganic thing. We don't need to go that far. All you need to really understand here to differentiate these is tetrahedral. It has 2 different groups, which is the 2 hydrogens. Okay? Did that make sense? Okay.
So it can't have a plane of symmetry to be a chiral center?
Exactly. If there's a plane of symmetry, you're not going to be able to establish a chiral center. You always have the ability to rotate it back into place. Okay? Okay, so dividing the ring in half, if we bisect the angle made by the 2 bonds of the ring in which the atom in question is involved, what we would see is that we're not actually going to have any planes of symmetry, are we? No. And what we're going to see is that each side is different for these things. Okay? And that's what gives the chirality, is the fact that each side ends up being different. You'll actually notice that if our hands had 2 thumbs on each side and were symmetric, we wouldn't have chirality, would we? Okay? This is actually why most like pencils and pens don't have chirality, because they have symmetry. Or for example, your chair doesn't have chirality because it has symmetry, right? Okay, so evaluating 2 sides of the ring. Does anybody need me to point out any more on these 2 ring sides, or is everybody okay? Of how those are very different, right? Okay. Some people do get stuck in the idea that, hey, it is the same group because it's a ring. It reattaches, right? But remember that we're talking about symmetry, right? We're talking about the inability to superimpose it, okay? It doesn't really matter if it reattaches to the other side. Okay, so this is a chiral center other than carbon. Nitrogens typically are a very common chiral center, especially in like biological molecules. They happen a lot. The nitrogen atoms can be sp3 hybridized, and therefore they can have tetrahedral geometry. Once they have tetrahedral geometry, then if they have 4 different things attached, they're going to end up being chiral centers, right? And this is actually reasonably common. This is the ammonium ion. And so there are actually quite a few quaternary ammonium ions that are chiral centers. You just have to have 4 different things attached to it, right? Okay. Notice one of those things could be a hydrogen. Right. So a molecule that has exactly 1 chiral center must be chiral. It automatically, by definition, ends up being non-superimposable. Okay? Let's talk about that other option that showed up. So remember, these were all branching options, right? Okay. And so, a molecule that has 2 chiral centers could actually be overall achiral. There is a way for that to happen, okay? So if we have two chiral centers, it could be chiral, or the molecule can be achiral. Achiral means what again? Not chiral, right? Okay. So a molecule is meso if it contains at least two chiral centers, but has a plane of symmetry that makes it overall chiral. So that's why we had been talking about this plane of symmetry before. So in this molecule right here, it has two chiral centers. They're still chiral centers. They have four different things. If you're just looking at that center being rearranged, it would still have chirality. Okay? But the molecule overall is achiral. And that's because when you look at this, the molecule actually can reflect across this plane of symmetry right here. Everybody see it okay? Okay. Okay, fantastic. And what does that refer to as again? Meso. Yeah, it's meso. Okay. Yes, indeed. Thank you. Let's go ahead and try this. Determine whether molecules A and B are meso. So, does everybody have what those look like in their heads now? Or down on paper so you can play with it? Okay. Unfortunately, I have to pay like $16 a month for me to be able to put figures in this. Yeah. I think we're good enough just like this, right? Okay. So, are A and B, is one of them meso? Are both of them meso? Is this a thing? Okay. Okay, let's go ahead and get it. Good. Okay. Fantastic. All right, so go ahead and put your answer. All right, so, yeah, A is meso. That was exactly correct. Good job. Why is it meso again? Yeah. So both of them had chiral centers around these two carbons, right? But in the case of this right here, we're actually symmetric, aren't we? Can everybody see that plane of symmetry all right? Okay. It kind of looks like a person, in fact, doesn't it? With their arms pointing towards you. Yeah. Okay. Any questions there? Fantastic. Okay, so the absolute stereochemical configurations are RS designators of the chiral centers. Each tetrahedral stereocenter is going to have two possible configurations. One configuration will be called R. The other configuration will be called S. One configuration is going to be the opposite or the inverse of the other. Essentially, they'd be mirror images of each other that are not superimposable, right? And this is what I've been talking about with chirality before. Now we're just going to learn how to name them, okay? So this right here is the R configuration. This right here is the S configuration. So you note if you do the mirror image of that, the mirror image of the R configuration has to be the S configuration, right? And vice versa. Okay? Because those are our only two options. Now, note that how do I go between these two things? Remember how I said you could always swap between the two configurations by doing what? Swapping any two atoms around the center, right? Yeah. So for example, here we have a hydrogen that's going away from us, right? That hydrogen and this chlorine up here are going to get swapped, and that's what we're seeing right there, isn't it? Okay. And that's how you always go between the two configurations. Okay, so this is the Kahn-Ingold prelog system. That's probably the last time you'll ever actually hear it referred to with its full name. From now on, you're probably always going to hear it as what type of stereocenter or what type of chirality. Nobody will probably ever use the name again. So we assign the priorities to the atoms surrounding the stereocenter, 1 through 4, to those substituents. The highest priority is going to be 1. The lowest priority is going to be 4. Typically, we don't actually have to do 4, because if we do 1, 2, and 3, what is the remaining 1? 4. Yeah. And the lowest priority 1 is going to be pointing away from us anyways, okay? As we're going to see in just a bit. So we're going to orient the molecules so that the highest priority ones are pointing towards us, and the lowest priority one is pointing away from us, eclipsed by the stereocenter. That means we actually don't see it, do we? Okay? So for example, kind of like a steering wheel, except the middle right here is a carbon, and the pole that goes into your car, that's usually a hydrogen, because that's usually the lowest priority one. Okay. We're going to observe the arrangements of substituents 1 through 3. We're going to assign that a configuration as R or S. If you had to guess from R, which direction do you think it rotates around for it to be an R? Yeah, right. Yeah. So if it's clockwise, right-hand rotation, R. Okay. The S is the left-handed or counterclockwise rotation. That's the chiral center S. Okay. And that's an example of it right here. Can everybody see it okay? Fantastic. Okay, so how are we going to assign these substituents priority? Well, we're going to do that based on the atoms at the point of attachment. So the atoms that have a higher atomic number are going to receive a higher priority. If two atoms of the isotopes of the same element, the atom with the higher atomic mass receives the higher priority. So say we had a carbon-12 and a carbon-13, which one would have higher priority? Carbon-13, right? The higher atomic mass. For any ties, we're going to have to go to the next step. Now, this is going to be a repeat thing where we're going to go out, out, out repeatedly, okay? At the same rate. So we're going to assign the substituents priorities based on the sets of 3 atoms located 1 bond away for the points of attachment. So you'll arrange the 3 atoms in each set in order from highest priority to lowest priority. You'll compare the first atom in each set and assign the higher priority to the substituent, the higher priority atom, i.e. the larger atomic number. Okay? And then you're going to go to the second atom, and you compare those if they're still ties. And then you'll go, which one has higher priority? And then you'll choose that one. And then you'll compare the next atom if you need to, and you just keep going like that. So basically, you just look for a tiebreaker. Is everybody familiar with doing something like that? Like you're playing rock, paper, scissors, and you just keep shooting until you get a tiebreaker, right? Yeah. That's all this is. It doesn't have to be made so complicated. We're then going to repeat steps 2A through 2B over and over and over until we get a tiebreaker, okay? Now, some of these, that can actually be a bit, right? And this is entirely due to the fact that sometimes we have chains, right? So if we have some fairly long carbon chains that we're going through, we may have to wait a while for a tiebreaker, right? But you don't actually have to go through these steps consciously every time. You will actually see in a bit that it becomes a pretty subconscious, very quick thing once you start going, okay? Okay, so the first thing we're going to do to try to assign this, it's RS configuration is we are going to go and we're going to go what has the higher priority around this stereo center. Where's the stereo center, by the way? Locator what? 3, exactly. So we go to carbon 3, that's our stereo center, right? That's the middle. Note, what is already in the back? Hydrogen, yeah. Automatically, if we just look at these, there's nothing that's going to be lower priority than hydrogen, right? So we already got that part taken care of, actually. Okay, and so the next thing we go is what has higher priority? Chlorine, carbon. Those are the things that are directly attached to this carbon center, right? Right here we have a carbon, here's a carbon, and here's a chlorine, right? So what has higher priority? What has a larger atomic number? Chlorine, yeah. And so that's priority 1, isn't it? Okay. Now we go to those carbons. Does carbon have a higher atomic number than carbon? No. Okay. Just testing. Every now and then, right? So we got to go on to the next atoms that are attached to those, don't we? So what atoms are attached to those carbons that are locators 2 and 4? There's another carbon attached to them, right? That'll be this one for this one, and over here for the other one. Yeah, so there's 2 is attached to the carbon 1, and 4 is attached to that other carbon there. So that's a tie, isn't it? Okay. We go again, and we go, well, there's 2 hydrogens there, aren't there? So those are also ties, aren't they? Let me point out that this is actually much faster than I just made that, okay? If we just look at these, automatically they're CH2 and CH2, aren't they? Those are the exact same things, aren't they? Like, there's nothing different attached to those. So if they look the exact same, we can just keep going. So we can just go on 1. Okay? See how I'm saying that this can actually get very fast? Yeah. So we just go out until they actually have something different attached to them. Okay. The next step out, we have a chlorine attached to 1. That would be our highest priority that's attached to that, right? On the other side, we only have a carbon attached to that one, don't we? Or do we? What's attached to this next one? So now we're at this point right here. And so what are we comparing as our highest priority in each of these? We compare a chlorine versus a bromine. Which has higher priority? Do you remember your periodic table? Which is lower on the periodic table? Bromine, yeah. So bromine has higher priority. Okay, and so that means this one over here is our 2. And then our next priority would be this one here, which is our 3. And what was priority 4 again?
So you start from the 3rd carbon, right?
Oh, I'm sorry. Yeah, I went too far, didn't I?
Wouldn't chlorine be tiebreakers?
You're right. You're right. I couldn't see past my own writing. Okay. Yeah. Let me go back here. So this is the first step right here. Those were equal. This one's the next step. And they're no longer equal, are they? So we compare the carbon to the chlorine. Right here. And the chlorine would actually have the higher priority. Let me go ahead and ditch my writing on here and go back in, okay? I'm actually having trouble seeing my own figure. Okay, so our first comparison was these two. Tie, right? our next comparison is those two, isn't it? Okay. Okay. And so we end up comparing the highest priority on each. That would be the chlorine versus the carbon, right? And so the higher priority for those would be chlorine, right? Okay. And so that's priority 1 there. This is priority 2 here. Priority 3. And then we would go priority 4, which is the hydrogen pointing away from us, right? Okay. Man, I really need that. But I don't have that with me. Sorry, I'm really, really spinning right now, and have for like 15 minutes now. Okay, so this is the priorities. Did I lose anybody in that? No, everybody's good. Okay. It's this tetrahedral group right here that has 4 or more different groups attached to it. Okay? Okay. And I think there was a...
So that's our configuration, right?
Yeah. Yep. That's your R configuration. You got it. Exactly. Yep. Going this direction, right? Okay. All right. That's just a summary of what we just talked about. If we wanted the S configuration, by the way, how could we do that? So you can't just flip the chlorine bromine. That wouldn't be stereocenters anymore. You would have had a configurational isomer, right? However, the chlorine and the hydrogens, if you flipped those two, you'd end up with the S. Yeah. And so if you went like this and this, that would be the S configuration, right? Okay. Okay. Now, how do we deal with double bonds and things like those? That's going to be our next thing. So when you have something like a double bond, right, you can't actually go item per item and compare them, can you? Because there's only one other carbon attached there. Yeah, there's 2 bonds to it, but there's only one other carbon. So what you're going to treat those like is if you have a double bond, you just count those twice. Okay? So when we're counting through our priorities, for example, this carbon right here, if we were counting our priorities, okay, we would treat that double bond as being it has a carbon attached to it, it has another carbon attached to it, and then it has the hydrogens attached. Okay? That making sense? So let's say we were trying to compare the priorities for that carbon right there. Okay. So you'd go the highest priority groups that are attached to it, right? And so what you do is you treat it like it has 2 carbons attached to it. You count the double bond, the 2 bonds in the double bond, twice. Okay? So instead of counting it as if it has a single carbon right there attached, you count it as if it has 2 carbons attached. Okay? Okay. So for example, this carbon right here, what would be the priorities of the groups that are attached to that? Yeah, so we would have the... Okay, so again, this carbon right here, right, we're counting that one. So the highest priority group that would be attached to that would be the oxygen, right? So we'd count an oxygen. What would be the next highest priority group? another oxygen because it has a double bond, right? And then we would start counting the hydrogen. Okay? Okay. Is that making a bit more sense?
Doesn't matter which oxygen. I figure the tiebreaker rule, right? So it'd be the oxygen to the right would be higher priority than the one above it.
Oh, it doesn't matter at all.
Oh, no.
Because they have the same atomic numbers. It would just be oxygen, oxygen. And then if you still needed more tiebreaker, you'd have to keep going. Yeah. And so then we'd start going, what's attached to the oxygen versus what's attached to the next thing on the other side. In that case, the oxygen would have carbons attached to it twice. Yeah. And so maybe it wins there. Okay, triple bonds would be what? Counting it? Yeah, 3 times. Exactly. You got it. Okay, so this right here, again, we're going to be figuring out that configuration for this chiral center. And so again, there's our chiral center right there. Can everybody see that okay? Okay. Okay, so automatically, what's the lowest priority one? Hydrogen. Yeah. Yeah. Everything else is carbons. That's hydrogen. Lowest priority right there, right? Okay. Then we go on, and what would be our next highest priority? The carbon.
To the left.
Which one's your left?
CH2.
Oh, okay. So the next highest priority is going to be, yeah, we look at this carbon over here versus the others, right? And that carbon's going to count as having 2 carbons attached to it, whereas the other ones would only have the one other carbon attached, right? And so our next highest priority ends up being that one right there, doesn't it? So that'd be our first priority. Okay. In fact, this one, the easiest one to identify would be the next lowest priority. Does anybody want to try to identify that? Yeah, the CH3 has to be the next lowest priority in terms of, like, priority 3, right? Yeah. And that's because it doesn't have any other carbons attached to it at all, does it? Yeah. Yeah. Just for your own edification, to try to speed problems up when you're trying to solve them, sometimes it's easier to actually work from the bottom priority up. So, like, just looking at the stuff that has nothing else attached is sometimes the easiest thing to do. Okay? So this has to be priority 3, and then that's left with priority 2, isn't it? Okay. Okay, and then we look at this, and what direction is that going? Yeah, it's going this direction, isn't it? Okay. Notice our hydrogen was already facing backwards, wasn't it? Our lowest priority group was already backwards. Okay? And that's actually very intentional for these first problems because it keeps you from having to do the rotations, right? And trying to figure that out. Okay, so if the fourth priority substituent points towards you, and you determine the first, second, and third priority substituents are arranged clockwise or counterclockwise, they're actually going to end up with the reverse arrangement before assigning the RRS. So imagine that this had the hydrogen pointing towards you. What would you have to do to try to figure this out? Yeah, there's 2 ways you could do it. You could either rotate the whole thing, right? And so you could literally take the molecule and just rotate the whole thing in front of you, right? But the easier way is to think of this kind of like a mirror, right? So if I'm looking at the back of something, like for example, I'm looking forwards right now, you're looking towards me, right? On the projector, when you say it's going left, what direction is that for me? Yeah, hold up your left real quick. Right? So the easy way to deal with those is actually just to assign them while they're facing the opposite direction than doing it. It'd be much harder to try to rotate the whole molecule, right, in a two-dimensional page. Just assign it, and then recognize that I'm the opposite direction, aren't I? So if it comes out R when you assign it, it's actually S, isn't it? If it comes out S when you assign it, it would actually be R. Yeah, because I'd be backwards. If the fourth priority substituent is actually in the plane of the page instead, you exchange the fourth priority substituent with the substituent that points away, and then you determine the first, second, and third priority substituents are arranged clockwise or counterclockwise, and then reverse that arrangement before assigning R or S. What was the rules for generating the other configuration? Exchange 2, right? So we're actually just abusing that, aren't we? So we're exchanging one of them that's in the plane with the one that points backwards. We exchange the lowest priority one in the plane with the one pointing backwards, right? And then we just recognize that because of that exchange, we're now opposite, aren't we? Okay? Okay. You could theoretically build a model, flip the model, and do that. Many books actually tell you to do something like that, and many professors would try to make you do that. It's extremely hard to do, and people mess it up almost all the time. Okay? This way you'll actually get it right. Okay? There's only about maybe 10% of people that can consistently get that right. Right? It's actually extremely difficult to consistently get right by trying to reflect them without a model kit. And if you try to do model kits, it just takes so long, right? Yeah. So here's actually examples of this. So we go ahead and go through this, and notice the hydrogen is pointing towards us in this case, isn't it? Okay. So we went ahead and assigned priorities to this. We have the first priority pointing away from us. We have the second priority in the plane of the page, right? And then on the left side, for me, we have the third priority, again, in the plane of the page, right? So our fourth priority is pointing towards us. Is that the correct direction to normally assign an R or S? No, it isn't, is it? So we go ahead and assign our R and S first. We have first going on to second, going on to third, right? And so we would normally assign that what? R. Okay? But we're actually backwards, aren't we? We're looking at from the exact opposite direction. So that automatically has to be the other one, S. Does everybody go with that so far?
Because the chlorine's pointing out.
Exactly. Yeah, the chlorine's pointing away from you instead of the hydrogen. Okay. Another way to think about this is you could actually exchange the hydrogen and chlorine, right? If you had exchanged the hydrogen and chlorine, then automatically that means those have to flip, don't they? Okay? So you can actually use that same rule that we come up with before, that we had understood before, to do this as well. Okay? Okay, so let's go ahead and look at this one. Notice the hydrogen here is, it's neither towards you or away from you, is it? Okay? It's in fact in the plane of the page, isn't it? All right. So we go ahead and assign these priority. The hydrogen's fourth priority. The carbon here is the third priority, right there. And this is the first priority. That's the second priority right there. Everybody see those okay? Okay, fantastic. So the first thing we're going to do before trying to assign priorities, because if you actually tried to count these out, it gets a little confusing. Like, you don't need to write the first and second on the right and left like that. You could have easily written it the other direction. Okay? And so it becomes incredibly confusing. You would go, oh, I don't know. I have a 1, then a 3, then a 4 here, and then the other side I have a 2. What the hell do I do with that? And so what you're going to do is you're going to take the hydrogen in the plane here, and you're going to swap it with the one in the back. Okay? And by swapping it with the one in the back, we now actually have something we can go ahead and assign in RRS. Okay?
So you're placing, so for chlorine, since it's pointing away, you're placing hydrogen to make it away.
Exactly, exactly. And then the chlorine takes wherever the hydrogen was, right? Yeah. Okay. Okay. And then what we're going to do here is we go ahead and sign it. We see the priorities end up going this direction now, right? So we normally would say S. But because we switched two different atoms around this central group, it's actually the opposite, isn't it? So we go ahead and answer R.
So why does it go first, fourth, second, not first, third, second?
You actually ignore the fourth. Because the fourth is pointing directly away from you. Okay? And that's one of the things that makes this so confusing when you look at like this one right here. Is remember that they are not pointing right and left, are they? They're pointing towards you and away from you. So you could write these reverse of each other. Okay? Yeah. So the fourth group always gets ignored. You never ever count that towards the rotation. Yeah. And that's why where we have to do all this stuff, where we have to swap the fourth group out so it's going away from us. Yeah. Yeah. It's literally an artifact of the fact that we're trying to do this in 2 dimensions. Yeah. If you were to sit there with a model kit, by the way, you could just always rotate the hydrogen away from you and always get everything right every time. Yeah. It's actually really easy with model kits. You can actually do it with your hand if you ever want. You can take little stickers, put it on in your hand, and then your wrist is actually the lowest priority group. And you can just line yourself up with the page and then just rotate your wrist away from you. Okay? By the way, if you ever get stuck on an exam or homework or something and you forget the rules, you can actually like label your fingers. Just do it. It will actually work every time. I know. Kind of funny, but it does work. Okay, so mirror images that are rapidly inconverted, the single bond rotations and nitrogen inversions. So if a molecule in its mirror image rapidly interconvert, then the molecule is effectively achiral. So for example, we can have the gauche right here. Everybody remembers your gauches, right? And these are your wonderful Newman projections. And then, well, what does that actually tell us? Those are conformations, right? Is that statically like that all the time? No, it's rotating, isn't it? And how quickly it's rotating depends on the energy, doesn't it? But usually at room temperature, those are actually pretty rapidly rotating, okay? And so what you're going to see here is that, yeah, that would have a chirality to it, but because these can actually rotate to go ahead and line up as mirror images, they don't end up with chirality overall. They actually end up achiral overall. Okay? And that's purely an artifact of the fact that, yeah, if you had the mirror image, yes, it would be different. But that rotation negates the difference, doesn't it? Okay. This is actually the interconversion by the chair flip, by the way. So right here you can see the cis form that's non-superimposable with a mirror image. But again, we have conformational changes here, don't we? This thing's not static and stuck in place. It's flipping back and forth every second. Okay? And so the chair flip actually causes these to be superimposable. Is everybody okay with that so far? Okay. So to actually have these non-superimposable mirror images that are meaningful, they have to be not something that can easily be interconverted. At room temperature, they're not going to be interconverted to each other. Okay? Okay, so these are Hawthorne projections. They're very helpful for determining your chirality of all the cyclic molecules because they take away the entire concept of chair conformations and interconversions, right? If they're non-superimposable as a Hawthorne projection, then they're going to be non-superimposable. They show you those planes of symmetry. Okay? So they simplify the chair conformation for your cyclohexane to a flat hexagon like so. And this will actually tell you if this is chiral or achiral. Notice here we have a plane of symmetry, so overall this is achiral, right? Over here we don't have any planes of symmetry, do we? And so this one can have chirality, can't it? Okay? When you end up with two different things that can't be interconverted. All right, so this is nitrogen inversion. The nitrogen atom in N-methyl ethylamine is actually potentially a stereocenter. The molecule is potentially chiral. I mean, if you look at it, right, we just count that lone pair there as one group, right? And can you see that you could easily have a reflection that couldn't be rotated to be superimposable, right? Can everybody see that okay? So why the hell was I talking about the tetrahedral stuff? Like, what the heck, Dr. Clausen? That's obvious. So the reason for that is those amine groups, those mean species, they can rapidly interconvert, and so you can't actually isolate the two. So you couldn't actually get the two chiral forms. Now, this actually starts bringing us into what in the world is this used for? Does anybody have any idea what this is used for? Anybody ever heard of a racemic mixture? No? Okay, anybody went to like a health supplement store? No? Oh my goodness. Nobody? The whole class? Okay, anybody ever seen health supplements being sold? Anywhere? On web? Nothing? Maybe? Oh wow. Okay. Are you at least aware that the, how about enzymes? Have you ever heard that enzymes react to different stereochemistries? Maybe? A little bit? Okay. I'll talk about this when we have it figured. Usually the health supplement store does it for me. There's DL supplements, DL alanine, racemic mixtures of proteins and amino acids. And you don't use one of the forms. You actually can't process it. But since apparently nobody's been to a health supplement store and has any idea about that, so we'll wait. Okay. So the nitrogen here is not actually a stereocenter, and this is because the nitrogen inversion causes any chiral centers to just invert. It typically happens at room temperature a fair amount of times every second. And so if you try to isolate one species from the other, you would end up with a species that's 50-50 after a while anyways. You just couldn't collect one of them from another. Okay? And again, that's a lot like the conformations. This is actually the nitrogen inversion from an orbital view. And so what we see here is this the sp3 hybridized nitrogen atom. And what happens is we can actually have that p orbital that was in the sp3 because it's just a lone pair, and lone pairs are very mobile and can move around really easy. We can actually have that revert back to a p orbital. Okay? Because it doesn't have a huge energy stability that it has to overcome. It's actually a pretty small variant. Because again, these electrons can flow very nicely and freely, right? And so what ends up happening is when it converts back to the p orbital, the electrons actually just pop over to the other side, and we end up back in a hybridized orbital, sp3, on the other side. Okay? And it just inverts between the two. And this happens at room temperature fairly often. Depends on the groups around it, but fairly often. Diastomers. This is going to be double bond configurations, and we need to talk about them in terms of your chiral centers. So diastomers are going to be stereoisomers that are not mirror images of each other. This was the cis-trans that we were talking about before. These can be diastomers. So again, these are not mirror images of each other. Everybody see that okay? Yeah. They're also not superimposable, are they? Okay, so diastomers. Again, these have the same molecular formula. They have the same connectivity, different molecules. So this is that other branching we were talking about. Okay? Okay, so we have a system to label these. You notice the cis-trans system works really good if you only have two things that are important, right? Has anybody gotten to stuff that has more than two important stuff around these double bonds? And went, wait a second, how the hell would that fit with cis-trans? That doesn't really make a lot of sense, does it? Uh-oh. So we do need another system. This is the ZE system for double bond configurations. We're going to determine the configuration around the double bond. First, we're going to determine which of the two substituents on the alkene carbon has the higher priority. Afterward, the configuration will be designated as Z or E, depending on the orientation of your two higher priority groups. All you need to do here is just determine the highest priority on each side. Okay? It's actually really fast and easy compared to the other ones. But first, we need to figure out Z and E. Okay, everybody say this with me. Ready? On Z same side. And so Z is on Z same side, right? Okay. Does anybody know why that's actually Z and E? This is German. Anybody heard of a Zweihander? Yeah? Yeah. Einhander, Zweihander. Means two and one. So Ein and Sein. Anyways. If you don't know that, on Z same side works so much better. Everybody can remember on Z same side? Okay, fantastic. E I actually technically remember because it actually kind of looks like it, doesn't it? It has a middle item surrounded by two other items. And so they're two different sides. So, I don't know. Weird thing about me, that's one of the ways that I used to remember this. Anyways, the highest priority group on the left side is going to be on the opposite side from the higher priority group on the other side. For E. On Z, they are on the same side. And so, that is that. Let's try this out. So, what was higher priority again, chlorine or carbon? Chlorine. What's higher priority, carbon or hydrogen? Carbon's higher priority. And so chlorine and hydrogen, chlorine and carbon are on the same side, and that means it is Z, same side. Yeah. If we have the chlorine again, highest priority, carbon, highest priority on that side, they're on opposite sides, so that's going to end up being E. Very good. Okay, we can also do this for rings, of course. And so we do have diastomers with no double bonds. They're in fact rings that make them diastomers because, again, rings still trap them on the same side or opposite sides, right? Notice this is just a more comprehensive naming system than we would do with cis-trans, right? Yeah. So if the two isomers are related by reversing the configurations of some but not all chiral centers, then the two molecules are going to be diastomers of each other. If the two isomers are related by reversing the configurations of all the chiral centers, then the two molecules are enantiomers of each other. And so this right here is diastomers, where we have converted one, but not both. Okay? And note that actually is, remember our rules before? We were talking about the inversion and what makes it an enantiomer versus non-enantiomer. That's the same rule. Okay? That's why the other one wasn't an enantiomer. It's actually a diastemer. Okay. Note again, these right here are diastemers of each other. So one of these matches up, the 1s. The 3r does not match up, does it? We've inverted one stereocenter. Okay? Okay. Very good. Let's go ahead and try solving this problem. I'll give you the figure here. Everything else will be down in the quiz part. Okay? You got that figure? Fantastic. So the question's going to involve, given this configurational isomer, 1-chloro-2,3-dimethyl cyclopentane, which the figure looks like so. Draw one of its diastemers. So go ahead and draw that out. And then we'll talk about the easy way to do that. Okay? What's the easy way to generate a diastemer? Okay, everybody got started drawing it and have enough of it that they can draw the diastemer of it? Excellent. All right. So what's the easy way to do this? Don't answer me yet. So how do we draw a diastemer? How do we interconvert these things? Okay. Okay. So do I want to swap 3 of them around, 2 of them around, an achiral center, a chiral center? What am I going to do? Okay. So you're going to want to take a chiral center, and you're going to want to swap 2. Why do you want to swap 2 around a chiral center? What does that do to the chirality? It goes from being an R to an S, doesn't it? Or an S to an R. Okay? And automatically that has to fill the diastereomer, right? So the diastereoisomer, you can always generate it by going ahead and swapping really any 2 of these. So if you just go ahead and swap, interconvert, say, one of the CH3s, that would work. You can interconvert 2. That would also give you another diastemer, wouldn't it? Okay. What happens if I interconvert all 3? Yeah, it's an enantiomer, isn't it? Yeah, I've done the reflection. Okay. Okay, so let's talk about some different strategies for success, drawing stereoisomers of a molecule with the chiral centers. So remember, a new configurational isomer can be obtained for each inversion of a tetrahedral stereocenters configuration. The number of configurational isomers that can exist is going to be double with the addition of each chiral center, because you could go through and invert each single one, right? And so the maximum number of configurational isomers that can exist for a molecule with in chiral centers is going to be 2 options to the power of the number of places those options exist, right? Just like if you were to flip heads and tails, okay? So the number represents the maximum. It does actually depend on your symmetry of your molecule, because some of the RS combinations can end up being meso, meaning those combinations are no longer configurational isomers. They actually come out of that, okay? So you may actually not generate all those as configurational isomers, and maybe some of them are meso, And you'll have to go back through and double check, are these meso to any of those others, if you were to generate all of these. This, by the way, is kind of an interesting thing. There was a program that was supposed to generate symmetry for molecules and figure out the possible configurations of the molecules that was going around about 5 or so years ago. Very, very popular, especially in Asia, super popular. Europe, kind of popular. The US, not as popular. But it had a huge problem, actually. And it could generate the maximums, okay. But it never, ever, ever, ever got the mesoisomers and all that stuff. So it never took those out. And so there was actually a run of about, I think we ended up doing 400 retractions because of that. Yeah, really brutal. Okay, so let's go ahead and go through the method for doing this. We identify all chiral centers, keep track of them. It's going to help us label the chiral centers 1, 2, and 3. So we can go, we're changing 1 now, we're changing 2 now, we're changing 3 now. Okay? Or keep track of them in some ways so you can figure out, I changed 1 and 2, I didn't change 3. Draw the first structure by specifying the configuration at each chiral center. We can use a dash wedge notation to specify each configuration. For the first structure, the choice of configurations doesn't really matter. We'll actually go back around and get it. Number 3, we're going to draw the second structure by reversing the configuration only at chiral center 1. Number 4, we'll draw the next structure by reversing the configuration at chiral center 2. We're going to repeat the configurations you drew for all other chiral centers in steps 2 and 3 here as well. So 5, draw the next 4 structures by reversing configurations at chiral centers 3, repeating those configurations. If you have to draw them all out, you can refer back to these directions, okay? It will help you structure it. And then you will continue this pattern for each remaining chiral center. The number of structures is going to double each time, so keep that in mind. Every single chiral center you draw out, you're going to end up doubling your entire structure set. Okay? All right. Finally, the last part is you always have to go back through all of your structures and compare them. This really, really helps if you've drawn them out in such a way that you can fold the paper to make columns, okay? And then what you can actually do is you can take the columns and basically run them through next to each other to see if they match, okay? This is not something that actually works so great digitally, by the way, because digitally actually has a lot of troubles, computers do, figuring out symmetry, okay? It's kind of like, why don't we have the like robots and self-driving cars and all that? Why is that not happening? Yeah, computers actually have a tremendous amount of difficulty handling three-dimensional information. Okay? It's actually really difficult to do. It's a hard problem, but cool problem. Just hard. All right. So here we have 3 chiral centers. Again, we have 2 options for each of them. They could be R and S, right? So we go 2 to the 3rd power. Therefore, there are 8 possible configurational isomers for this molecule. We go and label them 1, 2, and 3 so we can keep track of them. Okay? Okay, so the first one, well, we have this one right here. We have it where they all come out towards us, right? That's going to be our starting point. Why is that starting point? Because I felt like doing outwards towards us. There's no reason, okay? You got to start somewhere, right? Okay. Now, the next thing we're going to do is we're going to go step 3. So we take one of those, and what do we do to it? Opposite side. We swap the hydrogen that was going away from us with the bromine that was coming towards us, don't we? I did that for 1, chiral center 1, the first one on the left, because it's easier to keep track of. Okay? Okay, so the next step we're going to do is now we're going to have to go ahead and do the opposite configuration of the second group. So we take our two groups that we have so far, right here, and we go ahead and swap the bromine right there. And that's these. Everybody see I'm just systematically going through? Okay. Okay, so the next thing we have to do now is, remember, for each of these, we're actually going to have to do an additional swap, right? So for all the ones we've done so far, we now have to do one additional swap. So we take all of these, and we invert this one. Okay? And that's these four here. Notice that every single time after the step 3, you end up doubling. Okay? We then have to go through and double check and make sure we eliminate anything that's a mirror image and superimposable, that, you know, it's the same thing. Okay? All right, so there's going to be two conventions for drawing Fisher projections. Has everybody seen Fisher projections before? You guys ever seen what sugars look like in your textbooks? No? And they look like this kind of... Oops. No? Okay. You guys gotten into that in biochem at all? No? Okay. Well, yeah, most of you shouldn't be in biochem, but I'm just curious. So again, there's two different conventions for drawing the Fisher structures or projections. The intersection of your horizontal line and the vertical line is going to be a carbon atom. So where they intersect, that's a carbon atom. This is going to be typically an asymmetric carbon. The substituents on the horizontal bonds are going to be understood to point towards you. And so the ones that are coming out across are not actually in the plane of the page. They're pointing towards you. The ones that are these carbons going across this direction vertically are understood to be going away from you. Okay? Okay. And so notice it actually looks a bit like a bow tie, doesn't it? Yeah. So you got the person with the bow tie with the points coming out towards you, right? Yeah. Anyways, if it doesn't help you, then that's what it looks like. Okay. And that way we can quickly write many chiral centers. Okay? Notice that writing them out in semi-three-dimensional drawings would take a long time, a lot of effort, right? And be very difficult to actually do anything with it. So if we exchange any substituents on an asymmetric carbon in a Fisher projection, it's going to give the opposite stereochemical configuration. All we need to do is just take any of the horizontal and switch them. Typically you'll do the horizontal because there'll be rules for the vertical. Okay? However, theoretically, if you switch the vertical, that would also give you the different configurations. Okay? If you rotate a Fisher projection 90 degrees in the plane of the page, it's actually going to give you the opposite stereochemical configuration as well. Okay? Because you'd actually be flipping the whole thing in a mirror image. All right? That's actually how a mirror image would work for a Fisher projection, in case you're wondering. Okay, so these right here are Fisher projections for different sugars. And what we can see here is we can actually very quickly do enantiomers and diisomers of each other. Oh, yes we are. I'm a little bit over, aren't I? Okay, you all have a great day. We'll pick up from here, where we're going to start with sugars. Isn't that sweet? Ooh. It was such a bad joke. Yeah. So low effort. Uh-huh.